want to start out, of course, by thanking the Prototyping Tomorrow program for the funding. And I wanted to kind of start with my team slide here. This project's actually kind of been ongoing for a number of years, and this is the latest kind of team of it. We've had 3 postdocs cycle through, and also, of course, really a big thanks to the lab crew. They in this project, things get very messy, and it's a lot of hands-on work whenever we do an experiment, and also Jacob Piles for his support. So why concrete? It's the second most used material in the world. It accounts for 8% of global CO2 emissions. But important for us is that it's really the only current material system that can support construction scale additive fabrication. You know, we work in a lot of materials, and I think digital fabrication has enormous potential to revolutionize the building industry further, but concrete is really a material that the world is addicted to, and we have to recognize that. So why 3D printing? 3D printing has a huge potential to reduce material usage. Of course, it imparts all kinds of geometric freedom to design and also performance optimizations. We want to eliminate formwork. Formwork is by far the most significant cost, especially in custom concrete manufacture, anything more complicated than a wall. And we can look toward new ideas such as continuously variable mixed properties. This is still kind of on the horizon idea. And for our research as designers and fabricators, it's really this material that has a closed loop design and fabrication process, which I'll talk a little bit more about. Specifically, we're working with Dr. Victor Lee's revolutionary material, which is called ECC, Engineered Cementitious Composite. Cementitious composites are just a fancy word for concrete, but it includes other materials as well. They're highly ductile. That's the key thing here. So on the left, you can see a traditional high-performance concrete, very brittle in any kind of tensile or bending application, and on the right, ECC. That ductility being about 4%, which seems small, but that's 400 times larger than normal concrete. And it accomplishes this through pretty complex material science, but one thing to note is that it's about 2% by volume fiber. When I first heard that, I was like, well, that's not much at all, but we're talking about volume, and the fiber is very light, so it's actually contributes pretty significantly. But it's very difficult to print. I definitely want to underscore that. People have been 3D printing concrete for about 20 years now. You would think it would have made it well into commercial application. One of the challenges, of course, is that it's not a strong material in tension, and ECC has the potential to support that, but it's very hard to print. So challenges, how do you pump the material but still make it buildable enough to build up vertically? And a new challenge, which we've kind of started to work more on, which isn't highly documented in the literature, is this idea of shapeability. So how do you get good bonds between the layers? How do you reinforce these structures beyond the integral fiber we talked about? And a big one that we're very concerned with is the surface finish. I think this is kind of the elephant in the room with 3D printing concrete. And people talk about it at conferences to no end, but no one actually ever seems to solve it. So we'll talk about that a little bit too. And then, of course, scalability and deployment. So I'll jump straight into things that we consider our innovations in this project so far. Layer thickness variability is kind of a complex one, but it's somewhat new. The idea of shaping beads also been studied before, but I think we've developed a new twist on it. More accurate simulations and a kind of a side idea of printing on a mold. So I won't get into super high detail here, but this is related to how we layer these things. On the left is a variable layer depth caused by a consistent Z spacing on a curved surface, so this is a problem. The state of the art has kind of suggested the second approach, which is the layers vary along the surface, so consistent distance, not consistent height. And the last two are where we're working, where we're shaping the layer. The third one is showing kind of a corbelling effect like brickwork, but still a problem in the very last slide where we actually are printing in multi-axis with a shaping tool. And so what does shaping do? On the left is the kind of typical stack of concrete beads, which you've seen so much on Instagram, and on the right is the very subtle smile from me that you don't see much, which is suggesting that, wow, this is actually working. So just a quick 10-second video, hopefully. slow. Yeah, we learned a lot about tweening blurs thanks to DN. So here you can see a tilting path, following a shape, doing its best to make a smooth surface as it goes. And here, one of the panels. So looking more at a facade panel application, not as smooth in this case because of some other limitations, but you can see the optimized kind of ribbing that we're putting on the back, or the potential to be optimized.
So I'll just say that was fine.
Yeah, so I'm done in 2 more slides. So this is the flip side of that, so printing on a mold. So the simulation, we're actually showing how we shape these beads. That's been a big part of this, so we can do this in the computer and see it in real time. Next steps, hopefully you'll join us for an exhibition on November 1st, scaling this up, reaching higher fiber contents. And then just so far the outcomes, there's a joint Taubman CE Construction Robotics Lab opening in mid-November in GG Brown, as well as a couple publications and a disclosure. So thanks.